Welcome to this webinar on piezoelectric simulations using COMSOL Multiphysics. My name is Phil Kinane, and I'll be the host for this webinar. I come from the Boston office in COMSOL, and I'm joined by my colleague Supratik Dara, an applications engineer from our Palo Alto office. Supratik received his PhD in aerospace engineering from the University of Maryland in 2009. He was involved in research related to damage detection in composites, phase transformation in ferrous alloys, and design and nonlinear modeling of piezoelectric and magnetostrictive actuators and sensors. We're very pleased to have someone of Supratik's expertise to join us today to talk about piezoelectric simulations. Now, in this webinar, I will start by introducing the concept of multiphysics and how that works. Supratik will then introduce you to piezoelectric devices and what you need to think about theoretically when simulating them. He'll run a live demo simulating an example of a Tonpilz transducer. This demo has also been previously recorded and can actually be accessed from our website after this webinar. After this, we will answer your questions. And you may have noticed there's some small little box down there with your GoToMeeting controls where you can type in your questions and they'll be sent to me. You're more than welcome to type in these questions at any time through the presentation, but we'll get to them at the end of this webinar. Now, I can't really speak about multiphysics modeling without first touching on the subject of modeling itself. Firstly, we at COMSOL believe that modeling gives you insight into what your application is by providing an understanding of your device. What I've found is that with this understanding comes innovation. Modeling and simulation also lets you propose some designs and then tinker or optimize with them. A lot can be considered and achieved before proceeding to the expensive stage of building prototypes or deploying them directly to manufacture by using simulations. Finally, the real world may still be different than the simulations and prototypes would indicate. Working together with the testing and manufacturing processes, simulations allow you to test and verify the quality of the component or process that you are interested in. Now, computer simulations are not new and, in fact, have had a great history through the last 50 years or so. But up until a few years ago, mostly what people dealt with was single physics modeling. You just looked at one property of a component or a device. And if there are other physical processes that affected this device, you just made assumptions or approximations about them. Often the software packages you had to deploy that supported this modeling were different to each other too. Now, as you would know if you're working with piezoelectric devices, much of today's applications require multiple physical phenomena to be considered as part of the one simulation. To get a completely accurate simulation of your device's design, you need to consider all of the physics at the same time. So this is what we call multiphysics at COMSOL, and this is what you will see when Supratik gives his presentation. COMSOL Multiphysics does all of this, and it does so in the one unified GUI. It couples any physics you care to specify seamlessly, while also allowing you to enter your own arbitrary equations. As I said, this is all done in the one GUI on the same platform. There isn't any overhead for learning alternative platforms, and all of your modeling, irrespective of the physics, maintains a structural and visual consistency. Now, this is the COMSOL Multiphysics product suite, and it's applicable for modeling many different applications from all fields of engineering and science. At the top of the product suite, you can see the COMSOL Multiphysics base package. This is the engine for your modeling, including defining your own equations, meshing, solving, and post-processing. Underneath, all of the modules here contain user interfaces and predefined physics couplings for their specific application. For example, the structural mechanics, MEMS, and acoustics modules all have user interfaces for piezoelectric simulations. But all of the other interfaces in the other modules can be freely coupled to any of the others, so that if your device is better described by a nonlinear material model, then this can also be included in your simulation using the appropriate module. You can extend your modeling by making use of the optimization and particle tracing modules, while the LiveLink products are great for integrating your modeling with the rest of your product development workflow. This includes including your CAD geometries and pre- and post-processing through MATLAB and Excel. Now, before passing over to Socratic, I just wanted to briefly mention our magazine, COMSOL News. This is a free online resource that will let you read up on many different applications performed using COMSOL. For example, this article from the latest COMSOL News summarizes the simulation and experimental investigations of an energy harvesting MEMS generator. Through the transfer of mechanical energy to electrical energy using a piezoelectric material, the researchers here are able to power a tire pressure monitoring system. Using COMSOL, they are able to simulate the performance of these devices for different parameter values while optimizing their designs. They modeled the fluid structure interaction of the cantilever beam and its surrounding environment, and were able to determine the dampening of its deflection as a function of the tire pressure and cantilever beam thickness. I encourage you to check this and other stories out from COMSOL News. Now I would like to pass this presentation over to Socratic to talk about piezoelectric devices in detail.
Thank you, Phil, for the wonderful introduction to multiphysics simulation and for sharing that story on the energy harvester. Let me now get into some more technical details on simulation of piezoelectric devices. And let me start by introducing the piezoelectric effect. Piezoelectric materials convert electrical energy to mechanical energy and vice versa. The energy conversion is manifested as two different physical effects. The direct effect states that a mechanical stress can produce electric polarization in the material. This effect is used in sensing applications, as it is possible to measure a stress-induced voltage across the piezo material by connecting it to a suitable electrical circuit. The inverse effect states that a voltage applied across the piezo material will produce a strain proportional to the electric field. This makes piezo materials work as actuators as well. Since modeling the piezoelectric effect involves accounting for both structural and electrical effects, the simulation is inherently multiphysics in nature. COMSOL has built-in tools and interfaces for modeling piezoelectric devices. This interface provides a predefined multiphysics coupling between electrical and structural equations. The electromechanical coupling in piezoelectric materials is modeled using a set of coupled constitutive equations, as shown on this slide. Now, there are two popular forms of these equations that you might have often seen in the literature. One of them is known as the stress-charge form and the other as the strain-charge form. In COMSOL, you can choose to work with either of these forms depending on the type of material properties that are available to you for a given material of interest. In this way, you can avoid cumbersome pre-processing to convert the material properties from one form to another. So, why should we be interested in piezoelectric materials or modeling these kind of materials? Now, these materials are used in a variety of applications across different industries. For example, piezoelectric actuators are used in fuel injection systems and in the autofocus mechanism in cameras, digital cameras. Piezoelectric sensors are used in load cells, accelerometers, gyroscopes for sensing force, motion, and orientation, for example. Also, many MEMS devices, such as the ones used in our cell phones, use resonators and filters, and many of them work based on the propagation of bulk acoustic waves in piezoelectric materials. They are also used in acoustic devices such as hearing aids, acoustic logging tools in the oil and gas industry, and also for underwater applications such as in sonars and hydrophones. In order to efficiently and accurately simulate piezoelectric devices, we need to consider certain key elements in the process. I will talk about these factors and present some relevant examples in the next few slides. The first key element in modeling is to make an appropriate choice of the modeling geometry. Remember, the goal here is to get maximum information about the system with minimal computational effort. Hence, sometimes using a 2D geometry could be beneficial. If the device has an axis of symmetry, then you can also model it as a 2D axisymmetry problem where COMSOL will automatically recast the relevant equations in the cylindrical coordinate system. Sometimes it could also be useful to apply symmetry to a 3D model and represent only a chunk of the actual 3D geometry. This is shown in the picture of the composite transducer on this slide. It is also important to identify the piezoelectric as well as the non-piezoelectric solid materials in the device. COMSOL allows you to model such a mix of materials quite easily. When modeling laminated devices, extremely thin layers can be represented in COMSOL via the use of advanced structural and electrical boundary conditions, which can be assigned to something like a zero thickness geometric surface. This can be immensely helpful as you can save a lot of computational resource by not having to mesh such extremely thin layers. The next important factor is accurate representation of material properties. Piezoelectric materials are anisotropic, and COMSOL's architecture is inherently equipped to handle anisotropic material properties. You can even add mechanical, electrical, or electromechanical losses and damping. COMSOL also provides a library of material properties for 23 popular piezoelectric materials. You can easily view and edit their properties and also add your own materials in the library. One of the most important concepts when working with piezoelectric materials is the Poling direction. That's because this is what makes piezoelectric materials piezoelectric. The process of Poling aligns electric dipoles in the material, thereby imparting the desired anisotropy. In COMSOL, we assume a Z polarization in the material by default. However, there are many applications where the material could be radially polarized, or we may need to represent crystal cuts such as the AT cut or the BT cut. You can define coordinate systems in COMSOL using one of the several options available in the graphical user interface and use it to implement any Poling direction. This in turn saves your time as you don't have to manually transform material properties from one coordinate system to another. Another important aspect of piezoelectric modeling is to identify the physics setup or boundary condition. The challenge here is that we have to deal with not one, but actually two fundamental physics, structural and electrical. For example, while modeling an actuator, we need to apply an electrical load by specifying the voltage difference across the piezo. We also need to specify appropriate structural constraints in order to obtain the correct structural deformation profile due to the actuation effect. On the other hand, for sensing applications, we need to apply structural loads and constraints and also devise a way to measure the voltage drop across the piezo due to the applied mechanical load. Once you set up the geometry, material properties, and the physics and the boundary conditions, you also need to decide what type of analysis you want to perform. For example, a stationary or time-invariant analysis, that's something really easy to set up and very quick to solve. It is mainly useful for modeling quasi-static applications. For example, the shear bender actuator shown on this slide. But the static deformation or the static shear deformation of the embedded piezoelectric material creates a bending deformation of the entire composite beam. An eigenfrequency analysis is useful to get accurate information on resonance frequencies and vibration mode shapes. You can also use this to find Q factor or the quality factor and the decay factor in damped structures. It is also easy to set up such analysis. The solution time would typically depend on how many modes you are interested in finding and of course how large the geometry is and so on. A typical application could involve finding the resonance frequency shift due to a change in mass of a selectively coated cantilever type sensor that can absorb certain chemical or biological agents. A frequency domain analysis. That's something that is useful for getting the dynamic response of a vibrating structure. This allows you to see the performance at both resonance and off-resonance conditions over a desired bandwidth. The actual solution time for such models would depend on how many frequencies you want to solve for. COMSOL also provides advanced solvers such as the modal solver and the AWE solvers that can help reduce the computation time for frequency domain analysis. You can also perform a full-fledged time-dependent analysis if you're interested in capturing transient effects. The solution time will depend on how small a time step you want to resolve and how large a time range you want to simulate for. And finally, one thing that you definitely need to consider is the effect of additional physics in your analysis. For example, one of the design issues with high-frequency piezo oscillators is self-heating. Self-heating is just a name given to the phenomena of heating up of a vibrating piezoelectric material due to the structural damping and polarization losses. Such unwanted effects can degrade the performance of the vibrating material. In COMSOL, you can easily combine a piezoelectric simulation with a thermal analysis to quantify the effect of self-heating. Another such multiphysics simulation could include the combination of piezoelectric analysis with a full-wave electromagnetic analysis in an evanescent mode cavity filter. In such a filter, a piezo actuator is used to control the size of a small air gap, which can be used to tune the electromagnetic resonance frequency. Let me go ahead and present a couple of examples in a little more detail. Quartz oscillators. They are commonly used in many devices such as clocks and microbalance for high precision measurements. In this particular example, we are interested in modeling the frequency response of an 80-cut quartz that exhibits vibration in shear mode when electrically excited across its thickness. The response is tuned by adding a capacitor in series with the piezo device. The important modeling steps here include setting up an appropriate coordinate system to implement the 80-cut and finding the method to combine the finite element model with the lumped electrical circuit model, which can be used in turn to introduce the series capacitor. The 80-cut orientation is modeled by setting up a rotated coordinate system in COMSOL where we specify the value of the Euler angle beta to be negative 54.7 degrees. The material properties of quartz are then assigned to this coordinate system. COMSOL also provides an electrical circuit interface, which allows you to combine finite element model with lumped circuit simulation. In this case, the voltage source that excites the quartz crystal and the series capacitor are specified to be part of the lumped circuit. A bidirectional coupling between the finite element model and the circuit simulation is set up such that the capacitor acts as an inertial source for the piezoelectric model, whereas the electromechanical impedance of quartz affects the circuit model. In this slide, we see the deformation of the crystal at around 5 megahertz. The shear waves are clearly visible. The frequency response of the structural displacement of quartz shows how the resonance can be shifted by tuning the capacitor. Let's look at another example, a piezoelectric flow sensor. These are typically used to measure both the flow velocity and the direction in microfluidic devices and also in underwater applications. Since the fluid velocity is typically not periodic, we would have to solve this as a time-dependent model. We consider a simple geometry for the sensor to be made up of 2 layers, a compliant PDMS layer attached to a PZD5H layer. The sensor is placed in an open channel where the fluid comes in from one end and goes out from the opposite end. As the fluid pushes against the structure, stresses develop in the piezo layer, which in turn leads to a voltage difference across it. The key challenge in such a model is to simulate the fluid structure interaction and combine it with piezoelectric simulation. Furthermore, we also need to connect the PZT layer to a resistor in a circuit model in order to measure the time-varying stress-induced voltage. In this slide, I've tried to summarize the extent of multiphysics coupling involved in such a simulation. On one hand, the fluid load deforms the structure. As the structure undergoes large deformation, the computational mesh is altered using the moving mesh approach, and that helps us in accurately represent the change in the computational domain for the flow problem. On the other hand, the structural deformation also leads to the development of stress, which produces a voltage difference across the piezoelectric layer. This voltage is measured across a resistor connected to the piezo in a circuit model which is coupled to the finite element model. Now, the great news is that you can set up all these effects in a single COMSOL model and in a single graphical user interface and solve everything together to get a complete set of results from all the physics involved in one go. You don't have to worry about manually transferring data across multiple user interfaces, even for such a highly customized and tightly coupled multiphysics simulation. On this slide, we see the deformation of the sensor at different times. We also see in the plots on the right-hand side how the piezo sensor accurately captures the flow profile. Now, one of the interesting observations in the plot on the lower right corner is that the voltage response from the sensor shows a small drift over time. This is something that is characteristic of piezoelectric sensors. The drift can be tuned by altering the time constant of the sensing circuit, which in this case would involve changing the resistance connected to the piezo material. So we see that multiphysics simulations not only help us in quantifying expected behavior, but sometimes it also helps us to unravel and understand the underlying physics involved in the device design process. Now it's time for me to set up a live demo. In this demo, I'll be showing you how to model a simple Tonpilz transducer. Now the name Tonpilz is actually a German word which basically means sound generating mushroom. This type of transducer is typically used for relatively low frequency and high power sound emission. The transducer consists of piezoceramic rings stacked between a head mass and a tail mass. The transducer assembly is held together by a central bolt. The tail and head masses lower the resonance frequency of the device. Through this demo, we will learn how to couple structural vibrations with acoustic pressure in surrounding fluid media. We will also learn how to electrically excite piezoelectric materials and couple the structural vibrations between piezo and non-piezo solids. Our modeling geometry will include an aluminum head mass, steel bolt, a steel tail mass, and 4 discs of PZD4 stacked together. The outer curved surface of the tail mass is assumed to be fixed. The head mass is exposed to a hemispherical water domain. The outer layer of the water domain will be designated as a perfectly matched layer. This will help in accurate simulation of an infinitely extended region of water where the sound waves get absorbed as they travel far away from the source. In order to maximize the structural displacement and also make sure that the displacements are in phase, we need to have the polling direction to be reversed in alternate piezo layers in this stack. In COMSOL, by default, we assume that the polling direction is along the positive z-axis. We will find out how we can use a rotated coordinate system to create a negative z-polling direction. Before I switch over and show how to set up the model in COMSOL Multiphysics, let me go ahead and summarize the key modeling steps. I'll start by setting up the geometry, define certain selections of domains and boundaries for bookkeeping purposes. I'll define the perfectly matched layer to absorb outgoing waves and a rotated coordinate system to model negative Z polarization. I'll then specify the electrical, structural, and acoustic boundary conditions and also specify the material properties in the different regions in the model. Meshing is utmost important, especially when working on wave-type models. We will learn how to appropriately mesh geometry in order to accurately capture the waves. I'll solve the model as a frequency domain analysis and sweep over a range of frequencies. And finally, we will plot the solution to see some interesting transducer characteristics. Okay. Let me switch over to COMSOL. So now we are looking at the COMSOL desktop, and I'll start by selecting a 3D space dimension. Then as far as the choice of physics is concerned, I'll choose the acoustic piezoelectric interaction frequency domain and, of course, a frequency domain study. I'll start by adding a few parameters in the model, and I'll import them from a text file. I'll be using these parameters in different modeling steps later on. Then also let me go ahead and insert the geometry building steps. We have created the geometry in COMSOL Multiphysics using the built-in tools. The key idea here is to create a cross-section of the transducer and the water domain, and then basically go ahead and revolve that cross-section to get our 3D geometry. Now, as I mentioned, I'll be adding a few selections for bookkeeping purposes. Let me go ahead and add selection to start with. For example, I can group together these geometric domains and give them a somewhat more intuitive name. For example, water domains, and these are the inner domains. Now in this way, I also want to create more selections just to save some time. Let me go ahead and load up a model where I already have created these selections, and then we can take a look at how these selections look like. So these are the different selections that I'll be using while setting up the rest of the model. In the next step, I'll go ahead and add a coordinate system, the rotated coordinate system, change the Euler angle beta to pi. Let me also go ahead and add a perfectly matched layer, assign that to the outer layer of the water domain. These are the PML layers. Change the type of the PML to spherical. That's more appropriate, of course. And also tinker with one of the advanced settings here. It's called coordinate stretching. I'll change from the default polynomial to rational. That's actually more appropriate if you have a completely unbounded fluid region, just as in our model. Okay, so now once that I've set up some of these definitions, let me go ahead and go to our physics branch. This is the acoustic piezoelectric interaction frequency domain. And I'll make a few changes here, change the reference pressure to that of water. This is helpful when we compute the sound pressure level in decibels in post-processing. I'll also change the wave speed for the perfectly matched layer to 1500 meters per second. That's because we're dealing with water, so that's an appropriate number. Now, by default, COMSOL assumes that this entire region is made up of a fluid, and it would end up solving the pressure acoustics equation. Of course, we know that's not the case. So let's start customizing our physics. I'll go ahead and browse to the piezoelectric material branch and specify the positive z-fold piezo domains here. This is a better look of the domains that we have selected. I'll also add another piezoelectric material branch to specify the negative z-fold piezos. And for this setting, I'll also change the coordinate system to the rotated coordinate system. As I mentioned, this is going to help us in implementing the negative z-polarization. Then let me add a linear elastic material branch and assign the non-piezo solids. So these are the aluminum head mass, tail mass, and the bolt. So in this case, we are basically telling COMSOL that solve only the structural equations in these regions, whereas the domains that have been specified to the piezoelectric material branches, this is where COMSOL will go ahead and solve both the structural and the electrical equation. You can even take a look at this branch and see what COMSOL is going to solve. Similarly, in the pressure acoustic model branch, these are where our fluid domains are now specified, and COMSOL will solve the pressure acoustics equation. Now, one interesting thing to note is that COMSOL has also a default acoustic structure boundary where, based on how we have set up the domains, COMSOL automatically detected that this is actually the interface where the structure and the fluid they're going to meet each other, and we automatically put in the right equation so that the multiphysics coupling takes place. Okay, now the next thing that I'm going to do is add some boundary conditions. So I'll start by adding an electrical ground, assign it to these boundaries in the piezoelectric stack. Then I'll use a terminal boundary condition to assign the voltage to some of the other piezoelectric boundaries, and the voltage is going to be V0. This is one of the parameters that I had defined earlier. Then I'll add a structural boundary and use this to fix some of the side surfaces of the tail mass. And finally, I'll add a somewhat advanced acoustics boundary condition. It's called the far field calculation, which will help us to compute the far field pressure. Now, since we are only modeling half of the fluid domain, I'll put in this checkbox. I'll go ahead and click this checkbox for symmetry in the z equals 0 plane. And then I'll also change the type of integral to full integral. This is going to make it a little more computationally intensive, but on the other hand, this option will help us to compute the far field pressure, not only the magnitude, but also the phase, even outside, at any coordinate point, even outside our actual geometry, our actual modeling geometry. So that's a big advantage. Okay, now once that we have set up the physics, let me actually go back up to the definitions branch and add a few more steps. I'll tell you why I'm doing that. First, I'll go ahead and add something known as an integration coupling on the same boundaries or surfaces where we plan to compute the far field. And then I'll introduce a few user-defined variables. I'm going to load them up from a text file once again. And we will be using these user-defined variables to compute certain quantities of interest, such as the total radiated power and the directivity index. Then it's time to assign the material properties. So let me go to the material browser, and I'll start by selecting the material PZT4. Assign this to all the piezo domains. Back to the material browser. Select aluminum and assign that to the head mass. Then let's go ahead and select steel and assign that to both the steel bolt as well as the tail mass. And then, of course, finally, I need to select water as well and assign that to all the domains which are supposed to be water. So we are done with setting up the physics as well as the material properties. The next thing that I'm going to do is go ahead and customize the mesh. I'll start by telling COMSOL that I need to have a free tetrahedral mesh pretty much everywhere, but I don't want a free tetrahedral mesh in the region which I've assigned as the PML, or the perfectly matched layer. I'll also go ahead and create an extra size node, as we call it, and say that I want to customize the mesh size in the inner water domain. So I'll check this custom box and change the maximum element size to 1500 meters per second. That's the speed of sound in water divided by F0 max. What is F0 max? This is the maximum frequency that we intend to use in our simulation. It's a parameter I had defined earlier in the parameters section. I set it to be 40 kilohertz. And then divide that further by the number 5. So in this way, I'm ensuring that we end up getting 5 second-order mesh elements to resolve a wavelength. That's pretty good, and it satisfies what we call as the Nyquist criteria. Then let me go ahead and add a swept meshing feature, and also specify that I would like to have 5 layers of 5 equispaced layers of mesh in the perfectly matched layer region. So this is something that is suitable when you are using a PML. I'll also go ahead and add something known as a boundary layer mesh, and I'll assign that to the inner water domain. And as far as specifying the boundary layer properties, here I need to select the boundaries on which the boundary layer mesh will work. You can actually turn on the transparency and see that I've selected the interface wall between the inner and the PML water domain. And here I'll specify that I would like to have one layer and set the thickness of that layer manually to a value which is basically 1/100 of a wave. Okay, so once I build the mesh, if I zoom in, you can see that there is this tiny layer of mesh that I created here. Why did I do that? In this way, I can actually get more accurate computation of the far field pressure. Once I've set up the mesh, now we are almost ready to solve this model. Let me go to the study step, frequency domain, and set up the frequencies for which I would like to solve this model. And I'll sweep the frequencies within this range, starting from 3 kilohertz, step it up by 0.5 kilohertz, and go up to 40 kilohertz. Of course, the default here is hertz, so I'll specify the unit here, kilohertz. And then let me go ahead and click on this compute option. And in this way, COMSOL will start solving the model. Now, you can even track how we are solving the model by looking at this progress tab. And of course, needless to say, we are actually solving the model for a whole bunch of frequencies. So it's going to take quite a few minutes to solve this model. And I don't want you guys to keep waiting for that. So now that we know that COMSOL has started to solve this model, I'll go ahead and cancel the solution process at this point of time. And let me go ahead and open up solved model. This is just going to be like one of those Food Network show. And once I have the solved model open up, we can take a look at some of the important results. I'll start by showing you how the structural displacement looks like. So this is a scaled deformation plot. It's slightly exaggerated actually, the deformation. But this shows us how the structural deformation of the transducer looks like at 40 kilohertz. I can switch over to a different frequency, a much smaller frequency, let's say 8 kilohertz. And this is where we are, the structural deformation looks different. We are essentially looking at a vibration mode where we are looking at the actual vibration of the Tonpilz transducer. Let's look at a different plot. The potential plot here, we are looking at the electric voltage distribution in grayscale in the piezo stack. The arrows that you see, the red and the blue arrows, they actually show the direction of the electric field. And this is something that was desirable. We wanted to have opposite direction. The electric field should be directed in opposite direction, and that's what we are getting. This helps us in getting structural displacement in phase. Let's look at the acoustic pressure map at 40 kilohertz. Through this color setting, you can see the wave type effect in the water domain. So that tells us how sound waves are propagating. COMSOL also has some certain advanced post-processing tools. For example, we are now looking at what is called as the far field plot. So we computed the far field, and as I said, it's going to help us to compute or look at the far field pressure anywhere, even outside the modeling geometry. So that's what we are doing. We're actually plotting the far field pressure at a distance 1 meter away from the transducer, roughly speaking. And we are looking at the sound pressure level in decibels for an excitation frequency of 40 kilohertz. Once we change this frequency to a different excitation frequency, for example at 8.5 kilohertz, you end up seeing a different behavior of the far field sound pressure level. A more popular plot, especially for transducer designers to look at, is something known as a beam pattern. That's essentially looking at a section of this 3D far field plot. So let's look at the beam pattern plot. This is essentially a polar plot of the far field pressure. Once again, we are looking at the far field pressure at a distance roughly 1 meter away. And in this case, we are looking at the pressure in the XZ plane. So by changing this vector for the normal direction, I can control which direction I want to plot the beam pattern at. Let me go ahead and change the beam pattern. Let me go ahead and select a different frequency. So this is the beam pattern for 40 kilohertz. Let me select 7.5 kilohertz. Of course, the beam pattern looks different now. I could also change the directionality here. Instead of looking at the XZ plane, I can change the normal direction and look at the beam pattern in the XY plane. Let me quickly go through some of the other plots we have here. This is a combination of the near field and the far field pressure plotted together for 8.5 kilohertz. This shows the pressure on the axis of the transducer, also known as the on-axis pressure. Impedance, via the use of the terminal boundary condition that we use, COMSOL was automatically able to compute the admittance, and the inverse of that admittance is basically the impedance. Now, in certain cases, COMSOL might not be automatically computing what you really want to. For example, the TVR, we don't automatically compute that. But the good thing is, as long as you have an expression that you can type in, for example, this one, you can use that to go ahead and plot any quantity that you want. So similarly, we can plot a lot of other quantities of interest, for example, the radiated power and also the directivity index. And let me try and plot the directivity index here. Okay, so here's a plot of the directivity index as a function of the frequency. Okay. And now let me switch back to my slides and quickly summarize what we did in the demo. So we were able to see the structural deformation of the transducer and found out how it created pressure waves in water. We plotted the near and far field pressure along the transducer axis, also learned how to create beam patterns and plot far field pressure. We also saw how we can compute and plot certain other relevant quantities like the TBR, the impedance, and the directivity. Now, that's not it. There's more that you can do in COMSOL. It's also possible, for example, to perform advanced analysis where you can consider the effect of a prestress in the central bolt in the transducer and perform what we call as a frequency domain perturbation analysis. In that way, as you can see on this slide, we can find out the effect of an unstressed bolt versus what happens when you pre-stress the bolt on the frequency response characteristic of any quantity, for example, the PCR. You can see in this plot how they look different. Okay. I also wanted to let you guys know that we have a pre-recorded version of the demo that I showed a few minutes back on our website available. You can go and check out more detailed modeling steps there, and basically that's available at comsol.com/Tonpilz. Now, let me go ahead and pass it back to Phil. So, Phil, you're going to take it over from here for the Q&A session. And
yes, that was a great presentation, Sir Pratik. Thank you very much for that. We have a number of questions here that have come from the people out there. And the first one here is from Jennifer, and she's asking, is the frequency domain or a modal analysis used to speed up the solution time of a frequency domain analysis?
Yes, actually, I think this is something that I mentioned in somewhere during my presentation. Yeah, there are a few advanced solvers, for example, the frequency domain modal solvers, and also there is another one called AWE, or asymptotic waveform evaluation, I believe, was extension, one of those names. And both of them are certain other mathematical techniques that are also available in our product, and you can use them suitably to speed up frequency domain analysis.
Okay. Now from Tad here, in the piezoelectric sensor in the fluid showing voltage drift, I suppose that was before you built your demo, what aspect of the simulation of the PZ crystal gives that drift? Is there a time-dependent material property?
That's a very good question, and thanks for observing that plot in details. I'm glad that you posed this question. This is actually fundamentally electrical phenomena in some sense. That what we are looking at is we are looking at a time-dependent phenomena, and the time dependency can take place in a certain time scale, which can be shorter or much longer than the time constant of the sensor system, the electrical system involved in the sensor that we are looking at. And depending on the time scale that we are looking at, it's shorter or longer, you're going to see the drift or not see the drift. Essentially, that's something you can tune by adding an electrical circuit in your model, and also in real life by adding certain additional components in your circuit. So that's signal conditioning.
Okay. Bob comes with this question here. Is it possible to model photopiezoelectrics for optoelectrical transducers in fiber optics?
That's an interesting question. To be honest with you, I'm not too familiar with this application, but I would be happy to address this question offline. At this point of time, what I'm thinking is that basically this would be an extension of the piezoelectric simulation, just like I mentioned a few examples where you can combine the piezoelectric effect with another physics. Essentially, this is going to be something like that. So you'd probably have to combine the piezoelectric effect with a full wave electromagnetic analysis. So that would help you in modeling the optics part of it, the full wave electromagnetic analysis, and then the combination with the piezoelectric effect will help you to basically couple these two phenomena and see how you'd like to use the piezoelectric material to tune the optical effects that you're interested in. That would be the general approach.
I think I've seen examples anyway from the RF module of photonics where the waves are actually influenced by the structural geometries of the waveguides or the optic fibers. So I would say it's possible. That brings us to a question from Matt, rather similar. You mentioned that piezoelectricity can be modeled in 3 products. Does that mean I need all 3 of them? And well, I can say that you don't need all 3 of them, but there may be differences in the piezoelectric interfaces between the MEMS, the structural mechanics, and the acoustics modules.
Absolutely. As Phil pointed out, depending on what your greater modeling goal is, based on that you would like to choose which one of the modules or which one or more than one modules you would like to select from the COMSOL product suite. For example, the acoustic piezoelectric interface, coupled interface that I used in the demo problem, that is something that is uniquely available only in the acoustics module, because it's using one of those advanced acoustic coupling with piezoelectric. However, if you let's say on the MEMS module or the structural mechanics module, you would get pretty much all the features for handling piezoelectric material modeling, but you will not get that built-in acoustic coupling available. That's something unique in the acoustics module.
Okay. Here's a question that comes from Hugo, and he says, is it possible to simulate coupled transducers in a water medium? For example, if you wanted to send signals from one transducer to another, taking into account reflections.
Yes, absolutely. Yeah, that's very straightforward. It's basically it's exactly what I did in the demo problem. It's just that you need to add a second transducer in your model. That's all that you need to do.
Okay. We got a question here from Alvin, and he would like to know if you could explain just a little bit more about perfectly matched layer. And that actually relates to another question here about why did you determine the actual width of that perfectly matched layer? Why did you choose that dimension, if you like?
Sure. Yeah, both these are great questions, and without getting into too much mathematical details, if we put it this way, the perfectly matched layer is basically an option that it's a technical feature that you can assign to a domain which is working like an outer layer of your modeling geometry. The general mathematical technique employed in implementing the perfectly matched layer helps you to model the effect of absorption of waves. So you can imagine that if you throw a pebble in a pond, it's going to create waves, but as you go far away from your source of disturbance, the waves are going to die down. And the same thing happens, whether it's a pond or an ocean. And in order to model that in your computer, of course, it would be fairly crazy to draw an ocean and also a little transducer sitting inside the ocean. So that's kind of yeah. So in order to kind of address these kind of differences in scales in your modeling geometry, these advanced options are available. So basically to absorb waves, and in order to address the second question, that is how do we determine the appropriate thickness, that's typically based on the wavelength. So you would, roughly speaking, want to have thickness for one wavelength.
Okay, so now we have a question here from Lauren, and she would like to know that we showed examples where the input was voltage, but can we model devices where the input is a load?
Yes, and that actually takes me back to one of the examples that I discussed in a little detail. That was the flow sensor. So in that case, the input was actually a load, the fluid pressure acting on the sensor, piezoelectric sensor attached to the PDMS structure. That's actually a load acting on the structure, and that generated the voltage, which we actually measured using an electrical circuit model that we attached to the finite element model.
Oh, okay. So a sort of a follow-up to that probably is one here by Fred, who wants to know if you can introduce an eccentric load that you say if you had an error in machining that.
Absolutely, and this is where COMSOL is really flexible. As far as introducing the eccentricity, one thing that comes off the top of my head right now is in COMSOL you can actually type in any quantity, whether it is material property or in your case it would be force, you can type it as a function of the XYZ coordinate. So if you know what is the offset as far as the eccentricity is concerned, you can basically type in such an expression which is a function of XYZ coordinate, and that's pretty much it.
Okay. So we're getting a lot of good questions here. Another question here is from Mark. How can we plot displacement at a particular point as a function of frequency?
Yeah, this is a little bit of specific as far as going into the COMSOL interface is concerned. I believe you already have access to COMSOL, so I can give you the specifics. You need to create something known as a 1D plot group, and then you need to add something called as a point graph to that 1D plot group branch. And then in that way you can select whichever point you want to, and that's basically.
Sarif here wants to know, why did you apply a fixed constraint to the tail mass?
You can say that that's an arbitrary choice. The idea here is that basically, we are holding the transducer somewhere. It's not just floating in water. That's not typically what it is, what it would do. So it's definitely being held to the structure somewhere, and we are just modeling that as a perfect attachment. So the fixed constraint is working something like a perfect attachment to something else.
Okay. Fanny wants to know, can I model multiple layers of different materials?
Absolutely. Yeah, it's very similar to what we did in our demo model. Just like we had a head mass and tail mass made up of aluminum and steel, and then we had the piezoelectric layers, and they were even like reverse polarized and all that. So even if you have a like a flat structure, like a MEMS structure or something, and with multiple layers, different materials, you can absolutely go ahead and do it.
A follow-up to this comes from Aidan, who wants to know, is it possible to model complex piezoelectric structures such as piezoelectric fiber composites in COMSOL?
Yes, you can do that. There are certain ways of doing that, and when you say that you're working with composites, there are a lot of literature out there which will tell you how to find out average bulk properties of the material using different homogenization techniques. So there's a little bit of pre-processing that you probably have to do, and again, COMSOL's interface is perfect for that. You can type in any user-defined variables, as I showed in my demo, and that's basically the key idea. Once you have figured out what the average material properties are, what are the volume fraction of your fiber and the other materials, you can model it like any other structure.
Okay. Matthew wants to know if you can do the reverse. Right? Maybe that's piezo resistivity, I'm not sure. But can you do the reverse? Can you simulate the response of the piezo device according to a pressure wave? Can you get the voltage output over time?
Yes, absolutely. And this is, again, I have to go back to the same example that I stated some time back. It's very much similar to the flow sensor. In that flow sensor example that I showed, we modeled it in time domain. In to address your question, we would be modeling frequency domain, but the general idea is.
Okay. Breno here wants to know, is the acoustic module frequency analysis friendly for cluster computing?
Yes, and it's not only specific to the acoustics module, or not only specific to the frequency domain. In general, COMSOL is fully cluster enabled, so you can run any model on the cluster and get the maximum out of it. That being said, I can probably add in a couple of details here. Even if you're running COMSOL on single machine, on a single computer with multiple cores, our solvers are tuned to take the advantage of pretty much using all the cores. So that's automatic, and same thing. So you can, once you have a suitable license type, this is something you'd like to discuss with your COMSOL contact person, you can also run COMSOL on a cluster, and we don't have any restriction on the number of nodes that you can run. Similarly, we also have the option of where you can run your COMSOL model on Amazon EC2 Cloud. So that's a new option that we have started providing.
We have a question here from Dave, who wants to know, can you show the relationships as the electrode size is varied from tiny to enormous? Maybe that's multi-scale modeling, I'm not sure then.
Yeah, if I understand the question correctly, I believe what what you would like to see is that if I change the relative size or maybe the thickness of the electrode compared to size of the PCB layer or other structural components in my device, how would that change the response? Actually, there are certain interesting ways of studying that in COMSOL. We allow what is known as a parametric sweep over your geometry parameters. So if you create your geometry in such a way that you have parameterized the geometric dimension, then you can basically change the size of your electrode, the geometry of the electrode via a parametric sweep. In this way, you set up the physics, the mesh, the material properties only once, and you simply run this, run your model and use the parametric sweep to solve it for multiple cases. So it's basically like putting a for loop around your entire model, and then finally, of course, you can look at the plots in the post-processing. You can find out how the response changes as you change the parameters.
Okay. Ellen here wants to know, how does COMSOL handle piezoelectric stacks where the number of layers of the PCT is unknown, or if it's estimated?
Well, I guess we need to have some idea as to how many layers are there. If you really want to resolve each and individual layer, then that's like a design parameter. So it's probably a good idea to know how many layers we are planning to put in our device. If you do not want to resolve the layers, let's say for example, like they are really thin, and if you have a lot of layers, then you can again use a homogenized approach. You can just consider the whole thing to be one bulk material, providing you with a common providing you with one bulk displacement when you excite it. So that could be an alternate approach if you're not really sure how many layers are really there.
Okay. I think just a couple more, and then we'll have to wrap up here. But there's some questions here about the coupling to heat. And one of them is, during piezoelectric oscillation self-heating, do you account for thermal expansion? And if you do you assume density to be constant or mass to be constant?
That's a very interesting
tricky
question.
one for you.
Yeah, that's actually a really interesting question.
That's the best one for last.
Yeah, save the best for the last. Yes, you can combine your piezoelectric simulation with thermal and even find out thermal expansion. Now, that being said, there's one thing that as a researcher we have to keep in our mind, that the piezoelectric equations that we are solving, they are meant for small changes in the operating conditions. They are linearized constitutive laws, and if you go back to your thermodynamics book, the way these equations are derived, they are meant for small changes, or even rather constant temperature, to be honest with you, to be most accurate. So when you are looking at these kind of effects, these kind of multiphysics phenomena, yes, there are a lot you can do, but you also need to keep your mind open to interpret your results correctly. So that's the best advice that I can give.
Okay. And just to follow up on that, Christopher wants to know, for that type of modeling, what type of modules would you need?
You definitely need one of the modules which can handle piezoelectric modeling. It could be acoustics module, MEMS module, or structural mechanics module in the COMSOL product suite. As far as the heat transfer part of it, there's a lot that you can do in the base package of COMSOL Multiphysics. That's the big rectangle that you're seeing on your screen right now on the top. Depending on what advanced features in the heat transfer part of your simulation you're interested in, you may end up needing the heat transfer module.
Okay. All right, I think I'm going to have to wrap it up here. So that was a great Q&A session. There's just a couple more slides. I'd just like to conclude this webinar by inviting you all to join us at our complimentary hands-on workshops. They're run throughout North America, Europe, and the rest of the world. These workshops, you can get a chance to play with the software for a couple of hours while being instructed by one of our technical staff. They'll also be in hand to answer your questions that relate to your specific applications, which would be piezoelectricity probably in this situation. Then everyone comes away from these workshops with a trial license at COMSOL Multiphysics and access to our support staff during your 2-week trial period of the software. It's a great opportunity for you to get a feel for modeling and what it can do for you. And finally, you can, of course, contact us directly just by visiting our website. There's lots of different areas there which you can go in to investigate the software or contact us, contact support and the like. At the model gallery, which you can see here, you can access the actual model files and documentation for the demonstration model that you just saw Socratic build. And also, don't forget that link that Socratic mentioned, comsol.com/Tonpilz, to see the demo as a video, and all of the steps and so forth are included in that video. So that's it from us. Thank you, Socratic, and thank you all out there for your great attention. And we at COMSOL, we hope you have a great day. Bye-bye.
Thank you.